The fundamental theorem of algebra. The fundamental theorem of algebra states that if p of x is a polynomial of degree n greater than or equal to 1, then p of x equals 0 has exactly n roots, and this includes the multiple and complex roots. So how do we find the solutions or zeros of the function? The fundamental theorem of algebra tells us that because the degree is 3, we're going to have exactly 3 roots. So let's go ahead and find these roots. The first step is to graph the function on the calculator and find a 0. So our first step is to go into y equals and type in our equation. So we have x cubed plus 3x squared plus 16x plus 48. And then you want to hit graph. And then we need to calculate one of the zeros. So remember, we're going to find this in second trace and then calculate a 0. And then we want the left bound. So I'm going to keep clicking until we get the spider guy. He's on the left side of that x-intercept. And now he's on the right side of it. And then we guess and we get our 0, -3, 0. So the first 0 that we have is x equals -3, and we got that from the calculator. Then we want to verify by using synthetic division. So we're going to take that -3, box it, and then take our coefficients, 1, 3, 16, and 48. And then we're going to go ahead and divide. 1, multiply, add down, multiply, add down. And then when we multiply and add down, we want a remainder of 0, because when you have a 0 of the function, it has to divide without a remainder. So if this was not a 0, that would tell us that -3 is actually not a 0 of the function. So now that we've verified that -3 is a 0 using synthetic division, we want to either repeat the process, factor, solve, or use the quadratic formula to find the remaining zeros. So let's go ahead and write our function. Our remaining function is going to be x squared plus 16. Remember that 0 says we don't have an x term. Now, we only have 2 terms, and they're both perfect squares, but because we have a plus sign, we can't use difference of squares. So this one, it's actually going to be easier if we use square root method. So let's go ahead and set this equal to 0, subtract the 16 from both sides, and then we get x squared is equal to -16. Then if we take the square root of both sides, we get x is equal to plus or minus, remember, negative numbers come out as I, and the square root of 16 is 4. So we want to write our final answer, which is all the zeros of the function. We have x is equal to the one we found on the calculator, and then these 2 additional ones, positive 4i and then negative 4i. These are going to be the 3 zeros of the function. And just like the fundamental theorem of algebra told us, we would have 3 zeros of this function because the highest degree is 3. Let's go ahead and work through this example together. So first, let's find the solutions or zeros of the function. So remember, our first step is to take the equation and then graph it in our calculator and calculate a 0. So we go to y equals, clear the equation that you have, and then type in your new one, x to the 4th minus 4x cubed, and then plus 8x squared minus 8x, and then plus 3. And then go ahead and graph it. And all you really need to see is one of the zeros. And so it looks like it touches down. So this is going to look like a double root. So let's go ahead and trace the 0. And if we're on the left side, and then now we're on the right bound, and we hit enter, it gives us a 0 of 1. And so this actually is a double root. So remember, double roots, it means this is going to count twice. So I'm actually going to start writing my answers up here. X is equal to 1. So we need to verify that it's actually a 0 using synthetic division. So we'll put a 1 in the box, and our coefficients: 1, -4, +8, -8, and then +3. And then let's go ahead and divide. We'll bring down the 1. 1 times 1 is 1, and when you add -3, 1 times -3 is -3, and when you add, we get 5. 1 times 5 is 5, and when you add, we get -3. 1 times -3 is -3, and when you add, you get 0. So that's the 0 we were looking for. And then we mentioned that this was a double root, so I'm going to go ahead and try to divide this again by 1. So we're going to bring this 1 straight down, and we're going to ignore this remainder this time. 1 times 1 is 1, -3 plus 1 is -2, times 1 is -2. When you add down, we get 3. 1 times 3 is 3, and when you add down, we get 0. So that 0 remainder tells us that 1 actually is a double root. So we're going to take this remaining quadratic, and remember, we've done synthetic division twice, so we want to actually start with the degree that's 2 less than our original. So this is going to be 1x squared minus 2x plus 3. So this is what we're left with, and we still need to solve for the remaining zeros. And the fundamental theorem of algebra tells us that we're going to have 4 total. So we have 2, we need to find the last 2. And if you try to factor this polynomial actually doesn't factor. So we're going to need to use our quadratic formula for this. So a equals 1, b equals -2, and c equals 3. So let's go ahead and put that into our quadratic formula. X is equal to -b plus or minus the square root of b squared. So remember to put that in parentheses. Minus 4 times a times c all over 2 times a. So when we start simplifying, we have negative times the negative, which is +2, plus or minus, and when you put everything under the radical into the calculator, you should get -8 all over 2. And then when we try to simplify this further, the square root of 8 is not a perfect square, so you need to simplify the square root of 8, and you get 2 square root of 2. Now remember, because that was a -8, we also need to pull out an I over 2. Now we can simplify these 2's and these 2's, so we actually end up with 1 plus or minus I square root of 2. So I know I started writing all the roots up here, but I'm going to go ahead and write it down here where there's more space. Our solutions or zeros are going to be x equals 1, and then that double root of 1, and then we have 1 plus I square root of 2, and then 1 minus I square root of 2. And these are going to be the 4 solutions to our polynomial. That's it for this set of notes. I'll see you in class for more practice.